Welcome to the second part of the lecture series on semiconductor physics, where we will be continuing from where we left off in part 1 and talking about the types of semiconductor materials. So, intrinsic material is basically pure form of semiconductor material. It should have no impurities, it should have no defects in the lattice structure, and at 0 Kelvin, its valence band should be completely filled and the conduction band completely empty, right? However, at greater than 0 Kelvin, what happens is that electron hole pairs get generated, and from now on, we will be referring to electron hole pairs as carriers. Why? Because they are charged particles and they basically carry these charges throughout the lattice, so we will be referring to them as carriers. Now, basically, what happens is that the covalent bonds in the lattice break after the required energy, which we had learned in the earlier lecture, that was the band gap energy, is provided to the lattice, right? These excited electrons now become free and leave behind the empty state in the valence band, which we learned was hole. We have also, if you remember, treated these holes as particles. Even though they are simply the absence of an electron, we had learned that we can treat this absence as a particle with a positive mass and positive charge as well. Now, let's define a few things. So, these carriers, which are created in pairs, the electron concentration is always equal to the hole concentration. So, however much electrons we get in an intrinsic semiconductor will be exactly equal to the number of holes you get, and this we can refer to as intrinsic carrier concentration, or Ni. Thus, for intrinsic material, number of electrons, which is N, is equal to number of holes, which is P, which is equal to Ni. So we get this formula, which is N is equal to P is equal to Ni. Something that you will need to remember for solving numericals. Now, these carriers are not localized in the lattice. Instead, they spread out over several lattice spaces and are given by quantum mechanical probability distributions. So we can treat what Ni is as a function of the temperature. So you can see that Ni is equal to F of T, and this is basically obtained by the quantum mechanical probability distribution, once again, which is beyond the scope of what we are aiming to achieve here. To maintain a steady state carrier concentration, the carriers must also recombine at the same rate at which they are generated. So what happens is that we are aware that when thermal energy hits the lattice, the electrons basically get thrown off from the valence band into the conduction band, leaving behind an empty state called a hole. However, since the temperature is, let's say, maintained at room temperature, this process of generation of electrons and holes will continue at a steady rate. So we need to have a way to basically control it so that this Ni is fixed at a particular temperature. We know that Ni is fixed, so there should be a way that this process is controlled. That process, which we have already discussed earlier, is known as recombination, where an electron from the conduction band makes a transition. So either it will emit light or heat, as we have already discussed, and recombine with a hole once it reaches the valence band. So at equilibrium, Ri is equal to Gi, where Gi and Ri are the generation and recombination states. So basically, at a particular temperature, if you leave a semiconductor for a long amount of time, what happens is it attains equilibrium where we get a fixed Ni. And at this point, we know that the rate of generation of electron hole pairs and the rate of recombination of electron hole pairs are equal. Now, Gi with respect to T increases with temperature, and a new carrier concentration Ni is established such that the higher recombination rate RT balances generation. So if you increase the temperature, the rate of generation of electron hole pairs will obviously increase, which we have already discussed, because as we know that the more energy you give, the more bonds, covalent bonds can be broken, and the more electron hole pairs will be generated in the lattice. However, since the rate of generation is increased, after a certain amount of time, the rate of recombination also has to catch up to ensure that the Ni which is obtained at the temperature remains fixed. At any temperature, the rate of recombination is proportional to the equilibrium concentration of electron and hole and can be given by this formula. So this is a rather important formula from the point of view of numericals, and a lot of questions are asked from here. Now take a look at something which is very important given in this formula, which you should have learned in the chapter previous to this, which was semiconductor fundamentals. Take a look at the formula of Ri, which is the rate of rate of recombination. So that is given by alpha R, so the proportionality constant of recombination, times N naught times P naught. What is N naught? The number of electrons at that temperature. P naught is the number of holes generated at that temperature. What is to be noted here is that we know that N naught into P naught is equal to Ni squared. So for an intrinsic semiconductor, we are well aware that the number of electrons is equal to the number of holes, which we know is the intrinsic semiconductor density, or Ni. Now, if we multiply N with P, we should technically get N into N, or Ni squared. And since the rate of recombination is equal to the rate of generation, so we can also write that is equal to Gi. So hopefully I'm able to explain this formula. Now we come to extrinsic material. So in addition to thermally generated carriers, it is possible to create carriers in the semiconductor by purposely introducing impurities. Now this process of introducing impurities to the semiconductor so that we get carriers which are generated without thermal excitation is actually known as doping. Important definition from exam point of view. Most common technique for varying the conductivity of semiconductors. So generally we are aware that semiconductors resistivity or conductivity can be changed by changing the temperature. I hope you're aware that conductivity is the inverse of resistivity. But we can also change that by using impurities which we can add to the semiconductor. Now, the first thing is by doping, the crystal can be made to have predominantly electrons or holes. So basically we can see that even without any thermal excitation, the crystal lattice will by default have electrons in the valence band or holes, electrons in the conduction band or holes in the valence band, even without any thermal excitation and generation of electron hole pairs. So when a crystal is doped such that the equilibrium concentrations of electrons and holes are different from the intrinsic carrier concentration Ni, the material is said to be extrinsic. Now doping creates additional levels within the band gap. This is important. In silicon, column 5 elements of the periodic table, phosphorus, arsenic, introduce energy levels very near, typically 0.03 to 0.06 volt, the conduction band. So in silicon, once it's doped with column 5 elements of the periodic table, they introduce energy levels very near to the conduction band. So typically 0.03 to 0.06 electron volt. At 0 Kelvin, these levels are filled with electrons and very little thermal energy is required for these electrons to get excited to the conduction band. So basically what happens is that once doping is done and these additional energy bands are achieved, which we saw for silicon is very close to the conduction band, at very little thermal excitation, these electrons are able to jump to the conduction band, since we saw that the difference between conduction band and these additional newly created energy bands, which we saw was 0.03 to 0.06 electron volt, is thus very less. So the electrons can easily jump. Thus, silicon doped with donor impurities can have a significant number of electrons in the conduction band, even when the temperature is not sufficiently high enough for the in- intrinsic carriers to dominate. Now, N naught, so the number of electrons, is much greater than Ni, the intrinsic carrier concentration, and P naught, which is the concentration of holes, which means that it is a N-type material with electrons as majority carriers and holes as minority carriers. There is a very important and clear distinction here that needs to be made. The first thing is that when impurities are doped, even then at 0 Kelvin, the semiconductor will behave as a pure resistor. Second thing, once thermal excitation is provided to the semiconductor, the additional energy levels which are created from those levels, electrons will very easily jump to the conduction band. So the difference between an intrinsic and extrinsic material will only occur at very little thermal excitation from 0 Kelvin. And what happens is that we get a lot of extra charge carriers in the conduction band, and charge carriers in the conduction band are of course electrons. As a result, N naught, or the number of electrons in the lattice at, let's say here it was given 50 to 100 Kelvin, is much greater than what would otherwise have been the intrinsic semiconductor concentration, or P naught, which is the number of holes. And therefore we call these types of materials as N-type material. Now in silicon, if column 3 elements are doped, then they introduce energy levels which are very near the valence band. And what happens is that at very little thermal energy, so very little thermal energy is required for the valence band to get excited to these levels and leave behind holes in the valence band. So let's just go over what they are trying to say here is that at 0 Kelvin, new levels are introduced very close to the valence band when silicon is doped with column 3 elements. And thus, once very little thermal excitation energy is given to the semiconductor, electrons very easily jump to this new energy bands close to the valence bands and leave behind holes in the valence band. Therefore, the impurity basically allows the generation of a lot more extra holes. Since these levels accept electrons from the valence band, they are referred to as the acceptor levels. So, let's sum up what we have learned so far. So, semiconductors can be of two types, intrinsic or extrinsic. And in extrinsic semiconductor, they can also be of two types, p-type and n-type. What happens is that once the intrinsic semiconductor is doped with whatever type of material it's doped, it will create some extra energy bands. So if group 5 materials are doped, the energy bands will be higher up. If group 3 materials are doped, then the energy bands will be close to the valence band. The easy way of remembering this is that group 5 is higher, so 5 is a larger number than 3, so the energy bands will be higher up in the energy band diagram than the group 3 ones. So group 5 will be close to the conduction band, and group 3 elements will create energy bands very close to the valence band. If the energy levels are close to the valence band, then the electrons from the valence band can very easily jump to these energy levels, thus leaving behind a lot of extra holes in the valence band, and these extra holes can make us classify the element as p-type. Once the energy bands are close to the conduction band, then they can supply electrons to the conduction band at very little excitation, and this causes them to increase the number of electrons in the conduction band, and this is known as n-type semiconductor. Now, why the conduction band gets electrons while the valence band basically gives off electrons? we can basically understand once we deal with the exact atoms. So group 5 elements will form 5 bonds with carbon atoms or silicon atoms, right? So they have one extra bond for each carbon atom that is there, because carbon only forms 4 bonds. So there is one extra electron per, let's say, phosphorus atom when compared to carbon atom. This electron basically will be extra, that can be added to this extra energy band once the atom is embedded in the crystal lattice structure. Once again, exactly how this happens is very complicated and beyond what we are learning here. Now, rough calculation of the ionization energy can be made based on the Bohr's model for hydrogen atoms, considering the loosely bound electron orbiting around the tightly bound core electrons. Thus, E is equal to, so this formula exists, and this is the calculation of the ionization energy of the atoms. Now, something to be noted here is that questions may not ask ionization energy directly. They might use terms like donor binding energy. Once again, we have learned what are donor levels and what are acceptor levels. Thus, they should make sense. However, questions will often try to trick you. So, questions like this may come that calculate the approximate donor binding energy for silicon, and they have given all the values. You need to remember the formula. It's a very easy numerical, just you have to replace the values. Now, what is needed as extra knowledge basically is that you can just see what happens here. That doping creates a large change in the electrical conductivity. With doping of 10 to the power 15 per centimeter cube, the resistivity of silicon changes from 2 into 10 to the power 5 to just 5 ohm per centimeter. So basically, you do not need to remember the exact values, but this is just to show that with a very slight doping, how much the resistivity can be changed or how much conduction can be increased in a semiconductor. Okay, so when a column 4 material is used to dope 3 to 5 compounds, then they may substitute column 3 elements and act as donors, or substitute column 5 elements and act as acceptors. These are known as amphoteric dopants. The only key takeaway is that column 4 elements, when used with 3 or 5 elements, are known as amphoteric dopants. May come in an MCQ if it comes at all. Next, we move to carrier concentration. For the calculation of semiconductor electrical properties and analyzing device behavior, it is necessary to know the number of charge carriers per centimeter cube in the material. So basically, we need to know the exact number of charge carriers so that we are able to estimate the amount of current and the resistance or conductivity of the material. So this part is just basic theory which we no longer need. Now we come to one of the most important part of this chapter, from which multiple questions come and is very important, and it is known as the Fermi-Dirac statistics, the Fermi level and the graphs. It is very important that you have a clear understanding of what is happening here, otherwise it will be very problematic in the exam. Now, electrons in solids obey this said Fermi-Dirac statistics, right? Now, this accounts for the indistinguishability of the electrons. Basically, when they're in the conduction band, you don't know which atom came from which electron came from which atom. The wave nature that they execute or they show, and the Pauli exclusion principle. The Fermi-Dirac distribution function of electrons over a range of allowed energy levels at thermal equilibrium can be given by this very important formula. So Fe is equal to 1 by 1 plus e to the power E minus Ef by kT. Fe is the Fermi-Dirac distribution function of electrons over a range of allowed energy levels. Now it is important to understand this formula exactly. So Fe is basically the functional probability of finding electrons, which is equal to 1 by 1 plus e to the power E minus Ef by kT. E is the energy level which you are trying to analyze, and Ef is the Fermi energy level. What is the Fermi energy level? We will learn very soon. But a quick overview is that it is the average energy of all the electrons in the atom. So using this, we get a probability that an available energy state at E will be occupied by an electron at absolute temperature T. So our two variables in this formula is E, which is the energy state which we are checking for, and T, which is the absolute temperature at which we are checking the energy state. So EF, like I said, is the Fermi level, and it is the measure of average energy of electrons in the lattice. So it is an extremely important quantity. Now E minus EF greater than 3 kT, known as Boltzmann approximation. So Fe is approximately equal to EXP, so e to the power minus E minus EF by kT. This is referred to as Maxwell-Boltzmann distribution, followed by gas atoms. So just take a look at what is actually happening here. For gas atoms, Maxwell-Boltzmann distribution basically tells us that if E minus EF is greater than 3 kT, so 3 into K into T, we know K and T are both constants, then what we can do is we can simply ignore this 1 which is given in the formula. So if we ignore this one, we get 1 by e to the power E minus Ef by kT. Now we can flip it to the numerator and write this as e to the power minus E minus Ef by kT, or e to the power Ef minus E by kT. Both will bring the same things, and if you see the formula here, that is exactly what they have said. Now what if, let's say, E is Ef, so we replace E by Ef, and we can see that what happens is this term basically cancels out to 0, and we are left with 1 by 1 plus e to the power 0. So 1 by e to the power 0 is 1, so 1 by 1 plus 1 are half. So from that we can conclude that at the Fermi level, the probability of finding an electron will always be half, regardless of what we set the temperature to be. Okay, so now we have talked about how we vary E. Now if you remember, there are two more things which we can vary. One is K and one is T. So let's see what happens if we vary what is given here. So temperature. What happens once we change the temperature? Right? K is a constant. Sorry, I mistook it. K will be a constant. It's Boltzmann constant. What we are changing is T. Right? We have varied E. Now we are changing T, and we will see what happens. So T or is equal to 0 Kelvin. What will happen is the distribution takes a simple rectangular form. Let's see what happens. So if T is 0, this is 0, so we get 1 by 1 plus e to the power E minus Ef by 0. So basically we get 1 by 1 plus infinity, right? So 1 by infinity we get 0. So F is 0 if we get T is equal to 0. However, if we also take E is equal to Ef, then E minus Ef is 0, so we get a indeterminate form, right? So basically the curve obtains a rectangular shape. So I will just try and show the curve if it is given here. No, it's not given in the diagram, so I'll just show it later on. So just to show you guys what happens exactly at 0 Kelvin. So this is basically the graph that we obtained at 0 Kelvin. So we see that the probability is 1 before zero point 0.5 energy level, and then it drops to a sharp 0, right? However, if we change this to, let's say, t is equal to 50, how will this graph change? Basically, the graph becomes smoother like this, right? Now, let's say I do t is equal to 25. Let's use red. So then the graph is less smoother. However, they all will intersect at this point. So that is how the graphs will change based on the temperature of the semiconductor, which is varying according to our wish. Now, a very important property of the Fermi-Dirac distribution is that it is highly symmetric. Let's quickly take a look at the graph that we created. So if we see that whatever curve we were getting at this point is the same curve which we'll be getting at this point. And it is not only the curves, but also if you see the rectangular waveform, even that is symmetric. Whatever we get here is the same thing we will be getting here. So what we can say is that the Fermi-Dirac distribution is symmetric about this mean point. Also, one thing which we can note, let's say I consider this point. So whatever distance I move here will be equal to the distance I move here. If I keep this distance constant, then what I can say is that whatever value I obtained at, let's say, this point will be same as the value that I obtained at this point, except it will be the complement taken from 1. So I hope you understand what is the meaning of complement. So if I take f of, let's say, del EF plus E, so basically from the, sorry, I just made a mistake. So this will be del E plus EF. So from the Fermi level, I move slightly towards the right. So I just increase the energy slightly. This will be equal to the complement taken from 1. So 1 minus f of the same value if I move the same distance towards the left. So EF minus del E. So this proves the symmetric property of the Fermi-Dirac distribution. So from there we get this formula that f of EF plus del E will be the same as 1 minus f of EF minus del E. So basically the probability of finding electrons at a particular difference from the Fermi-Dirac from the Fermi level will be the complement of 1 of the probability of finding electrons from the Fermi level in the opposite direction. So the curve is basically symmetric. Now, is it odd symmetry or is it even symmetry? It is odd symmetry because we need to take the complement. This symmetry makes the Fermi level a natural reference point for the calculation of electron and hole concentrations. Now, note that Fa is a probability of occupancy. Thus, if there is no available state at E, there is no possibility of finding an electron there. For intrinsic materials, the Fermi level lies close to the middle of the band gap. The difference between the effective mass of electrons and holes account for this small deviation from the mid gap. In n-type materials, the electrons in the conduction band outnumber the holes, thus the Fermi level lies closer to the conduction band. Similarly, in p-type materials, the holes in the valence band outnumber the electrons, thus the Fermi level lies closer to the valence band. The probability of occupation Fe in the conduction band and the probability of vacancy 1 minus Fe in the valence band are quite small. However, the densities of available states in these bands are very large. Thus, a small change in Fe can cause large change in carrier concentrations. So let's summarize what we have learned about Fermi level so far. What is Fermi level? It is the average energy state of electrons in a semiconductor. For p-type semiconductor, it will lie close to the conduction band, to the valence band. For n-type semiconductor, it will lie close to the conduction band. We learned that this Fermi-Dirac distribution is highly symmetric. So wherever you move from the midpoint, you will get odd symmetry about that point. So you have to take the complement of 1, since probability is range is from 0 to 1. So you need to take the complement of 1 and you will get the probability in the opposite direction. Also, we learned that this Fermi level can be used to estimate the energy of electrons at 0 Kelvin, since what we can do is at 0 Kelvin, the probability of finding electrons will simply represent a rectangular shape. And at higher temperatures, the curve will start to get smoother. So then comes this diagram, and this is actually rather difficult, so we will go step by step and deal with it individually. So let's first go over the first column, which deals with Ne. So Ne, if you see here, is the density of states. So let's talk about what is happening. So sorry, this is the second column. We will first discuss the first column, so this part. So take a look at what they have tried to show here. You have EC, EV, and then a dotted line. And in all the three materials, so intrinsic, extrinsic N-type and extrinsic P-type, you have these three lines. So EC, or the uppermost line in all the curves, represent the conduction band energy. EV similarly represents the valence band energy. So what does the dotted line represent? So you can see here, it represents EF, or the Fermi level. Now, as we have already learned, for N-type semiconductor, the Fermi level is close to the conduction band, and for P-type, it is close to the valence band. Now, talking about the second column, which we saw was density of states, or Ne. Now, if you take a look at all these three curves, they're practically the same, and that is what is actually expected. Why? Because let's first see one of the curves. So this x-axis shows us the density of states, so Ne. This y-axis shows us the energy band, which we have seen here. Now we see that, so this side is increasing Ne and this side is decreasing Ne, and this side is increasing energy, this side is decreasing energy. So in the conduction band, as the energy increases, the number of available states also increases. And in the valence band, as the energy decreases, the number of energy states also increases. So in valence band, with decrease in energy, the number of energy states increases, or the density of energy states increases. And in the conduction band, with increasing energy, the number of, or the density of states Ne increases. So this remains constant throughout all the three types of semiconductors that are shown here. Now we come to the Fe, or the Fermi-Dirac distribution, and we have already discussed, or I have already shown you the graph of Fermi-Dirac. Now this is not at 0 Kelvin, which we can already understand since it is not a rectangular curve. But let's see what is happening. So once again, if you see the Fermi curve, it is same for all the three except that it is shifted. So for the p-type semiconductor, it is closer to the valence band. For the n-type semiconductor, it is closer to the conduction band. And for intrinsic semiconductor, it is in the middle. How can we explain this? See, we know that at Fermi level, probability of finding an electron will be half. And when this energy is equal to EF, we need to ensure that this probability is 50%, right? However, when you shift, so this x-axis represents the probability and this y-axis represents the energy. So regardless of wherever EF is, at EF this needs to be 50%. As a result, what happens is when the Fermi level itself is shifted upwards, let's say for n type, when like we saw, the entire Fermi Dirac distribution curve gets shifted upwards, right? So the probability of finding electrons in the conduction band actually shifts up, so it shifts to higher energy levels. And therefore, at these energy levels, the probability of finding electron actually increases. And the same thing, the opposite actually happens for holes. So from this, we have understood the probability distribution versus energy relation. Basically, you need to remember that whenever the FE gets shifted, that's exactly how the curve will get shifted. So if the curve is asked, the very basic way to draw is drawing the Fermi level and treating it as an intrinsic semiconductor, drawing the curve, and then marking the valence and conduction band according to P or N type. Now we come to carrier concentration. Once again, this is very easy to understand. Basically, we are aware that the carrier concentration will be more number of holes for P type, more number of electrons for N type, and equal number of holes and electrons for uh, intrinsic semiconductor, and that is exactly what is shown, right? Now, important thing to note is that these do not attain their peaks at the valence band energy level or at the very extremes. They attain their peak somewhere in middle. This is important. Also note that no part of your curve should come between this, because that is the forbidden energy gap. Now, since Fe is symmetrical above EF, a large electron concentration implies a small hole concentration and vice versa. So, if Fe is symmetrical about EF, a large electron concentration implies a small hole concentration. So, if the curve is shifted downwards, then lower part of the curve actually stays in the conduction band and a higher part of the curve enters the hole band. So, sorry, not the hole band, the valence band. Therefore, we get a large number of holes. So, the curve is shifted upwards because the Fermi level is shifted upwards. Then the large part of the curve now enters the conduction band. These curves are not to scale, they are not perfect, but you can understand what is happening. So, as a large part enters the conduction band, a large number of electrons are there in the conduction band. Therefore, lesser part of the curve lies in the valence band, so lesser number of holes in the valence band. Thus, EC minus EV gives a measure of N in N-type material, and EV minus EF gives a measure of P. So, what is EC or EV? We know EC is the conduction band and EV is the valence band. So, energy of the difference of energy of conduction band and Fermi level gives a measure of the number of electrons, and difference in the energy of valence band and the Fermi level gives a measure of number of holes that are there in the extrinsic semiconductor. So electron hole concentrations as equilibrium, the FD distribution function can be used to calculate the electron and hole concentration in semiconductors if densities of available states in the conduction and valence band are known. So in equilibrium, the concentration of electrons in the conduction band can be given by this formula. So integration of from conduction band energy to infinity of the Fermi Dirac distribution probability times capital NE, so the density of states, times DE, which is the delta of the difference in energy, where NED is the density of available states per centimeter cube in the energy range DE, right? So that's exactly what I mentioned. Now, upper limit is theoretically not proper since the conduction band does not extend to infinity. However, since Fe decreases rapidly with increasing energy, the contribution to this integral for the higher energies is negligible. So, Fe, as you can see, it increases very steeply as you approach 0. So at higher energy levels, it is basically negligible, and so we can simply ignore the fact that we are taking the energy level to infinity, right? So if we will very quickly approach zero, so at higher energy levels, it does not make a change in the integral. So we can simply ignore that fact that we are actually not taking proper limits. EC is proper, however, the infinity limit is not proper, but we can simply ignore that fact. So using the solution of Schrodinger's wave equation, it can be shown that LE is equal to 1 by 2 pi square to m star. Note that m star is the effective mass formula which we had seen earlier, divided by reduced Planck's constant square. So h by 2 pi is h bar, or reduced Planck's constant, to the power 3 by 2 times e to the power half. So that is the probability density, the density of energy states at an energy level, which we can calculate using this formula. Once again, important from a numerical standpoint. Okay, now mathematical simplification can be made assuming that all available states in the conduction band can be represented by an effective density of states Nc located at the conduction band HEC using Boltzmann approximation. Therefore, we get the much simpler and much more useful formula of N naught is equal to Nc e to the power minus Ec minus Ef by kT. Now, if you remember, the Fermi-Dirac distribution formula was Fe is equal to 1 by 1 plus e to the power E minus Ef by kT. And we have seen that approximating that, we can get that Fe is equal to e to the power minus E minus Ef by kT. Since we are taking the distribution of the conduction band, we are basically doing Ec minus Ef. So we are replacing E by Ec in the formula, and Nc is the basically simplified form of the energy level which we are taking. So basically it's the effective density of states Nc located at the conduction band H. So we are calculating and taking the density of states at the edge of the conduction band, which we are representing by Nc, and we have this formula for Nc from the original expression that we had obtained. Note how this function changes. As Ec minus Ef decreases, Fermi level moves close to the conduction band, the electron concentration increases. So since this is e to the power minus Ec minus Ef, so this is basically 1 by e to the power Ec minus Ef. So if Ec minus Ef decreases, so e to the power, this term will decrease. So the denominator decreases, the entire term actually increases. Therefore, we get a higher electron concentration. And by similar arguments, we can get the basically we are changing the same formula. Nc we are changing by Nv. So the effective density of states located close to the valence band, and we are replacing Ec by Ef, basically in the Fermi-Dirac distribution, replacing E by Ef. Replacing E by Ev, the valence band conduction level. Okay, there is a slight mistake, I think, in the formula. This is wrong, I think. No, it's correct. So it's Nv into 1 minus f of Ev. So f of Ev we know was e to the power minus Ec minus Ef by kT. So it is 1 minus, therefore we get this formula. Mv into e to the power minus Ef minus Ev by kT. Note that these terms are different. Originally we got Ec minus Ef. However, for p types or holes, hole concentration formula, we get Ef minus Ev. Since the Fermi level here lies above the valence conduction band, right? If we took Ev minus Ef, this term will become negative. So that will be wrong. The only terms separating the expression for Nc and Nv are the effective mass of electrons and holes respectively, since Nc and since hence Nc I think should be equal to Nv. That's what they are trying to say here. So Nc and Nv, if you can see here, they are trying to separate. Basically what they are trying to say is here we have n star n square n star n, and if we take nv we would get n star p. So the effective mass of holes and effective mass of electrons, those are the things which will basically change between nc and nv, right? Otherwise all of the rest of the terms are constants. Now for intrinsic material, EF lies at the intrinsic level EI, very near the middle of the band, and the intrinsic electron and hole concentration are given by this. So the same formulas, right? So first time we get EC minus EI by KT. We are basically replacing EF by EI here because the Fermi level lies very close to the intrinsic level EI, which is the middle point of the valence and conduction bands. So keep that in mind that for intrinsic semiconductors we can write the Fermi level as basically being the midpoint of the conduction and valence bands. Now at equilibrium we know that N naught P naught is constant, so Ni square is equal to NCNV e to the power minus Eg by Kt. Once again, a very important formula that we obtain, that N naught into P naught is Ni square, which is equal to Nc, which is the energy density very near to the conduction band or at the edge, Nv, which is the energy density or the energy state density very near to the valence band, times e to the power minus Eg by Kt. This equation gives an expression for the intrinsic carrier concentration Ni as a function of Nc and V and temperature. So we get a formula of Ni which we were trying to find as Ni is equal to root over Nc Nv e to the power minus Eg by 2 Kt. So finally, after all of this headache, after going over statistics, going over so many graphs, we have found an expression for Ni which will allow us to estimate the carrier concentration in a semiconductor given that we know the temperature. Alternately, we can also get these expressions for N naught and P naught. Once again, we are deriving from the fact that Ni is equal to this, so we are basically replacing that in the formula for N naught and P naught, and we get these formulas once again important from numerical point of view. Here's an example question which is given on this topic. Once again, we can simply skip this. This question is important, however, you can do it on your own. I'm not discussing it here. Temperature dependent of carrier concentration, only this formula is important. However, the rest part is not part of the syllabus which is provided. I may make another video on it. But that's it. We are at the end of the chapter. So thanks for watching.